Hi, chemistry class. This is your first vodcast of the school year. I'm going to be doing this on and off throughout the school year. This is just an introductory chapter, but there'll be some chapters where I present content, and then you come to school and you do your homework at school. That way you do the hard stuff with me, and I just present some information for you at home. At your leisure, you can scroll through, you can skip me, but I am going to hold you accountable for the content. So you decide how you want to work this. Like I said, this is just the introductory chapter. And the first chapter is kind of review, a little bit on scientific method. But remember, we're doing the candle lab and I'm tricking you into finding the equation for combustion of a candle. Well, let's get started. Your book starts off and it talks about a story of two chemicals, two unrelated discoveries that form the basis of an important environmental issue. I'm sure you've heard of ozone depletion. So let's look at it, and it's actually changed over the last couple of years. So I want you to watch a 4-minute video. If you don't like the sound of this, you can just go to YouTube and find the video, whatever happened to the hole in the ozone layer. Here's the video.
Gotta get rid of that hole in the ozone layer, you know, that's some serious stuff.
Hey, that's not a thing anymore.
What? It's gone? Howdy, chlorofriendicarbons. You've found your way to D-News. Thanks for that. Welcome. I'm Trace. If you are a millennial, you've probably spent your whole life hearing about the hole in the ozone layer. Before you can understand the hole, though, you gotta know what the ozone layer is. The ozone layer isn't really its own thing. Instead, 90% of our ozone floats around in the stratosphere, about 6 to 30 miles above our heads. Ozone is 3 oxygen atoms linked together, O3. When in the stratosphere, ozone absorbs harmful UVB radiation, protecting us and other life here on the ground in the troposphere. In the late 19th and early 20th centuries, people were just beginning to harness the power of refrigeration using toxic gases like ammonia, methyl chloride, and sulfur dioxide. In 1928, an enterprising inventor at General Motors created a non-toxic chemical for refrigeration called CFC, chlorofluorocarbon. It was patented as Freon by DuPont and sold in air conditioners, fridges, bug sprays, spray paints, hair conditioners, and healthcare products. At its peak, companies were making 1 million metric tons of CFCs every year. Sure, at sea level, CFCs are non-toxic and safe for humans, but if they get into the upper atmosphere, they're subject to photodissociation, where UV radiation breaks a chlorine atom off the CFC. If that free chlorine finds a molecule of ozone, O3, it will react with it, destroying the ozone by ripping off one of its oxygen atoms to make chlorine monoxide, leaving regular old O2 or oxygen in its wake. Then the chlorine monoxide gets hit by UV and broke up again, so it has to find another O3 molecule to try and stabilize it, and the cycle repeats itself. It's bad. In 1977, we were studying the ozone layer and it was fine. By 1981, there were hints that something was amiss. Then in 1984, scientists suddenly registered a giant hole in the ozone layer. They published their findings, and in 1987, the Montreal Protocol was signed, beginning the phasing out of CFCs shortly thereafter. Meanwhile, even though the house was clearly on fire, DuPont and other companies insisted everything was fine and fought tooth and nail to keep CFCs legal. But they finally relented after scientific evidence became indisputable. A looming environmental disaster that pitted corporations against the scientific community. Where have I heard that before? Though CFCs can hide in the atmosphere for 40 to 150 years, without the emission of new CFCs, eventually that free chlorine cycle will stop. If the chlorine runs into some methane up there, it would break up, forming hydrogen chloride, which is stable enough to rain back down to Earth. In 2015, about 30 years after the protocol was signed, the ozone hole reached the largest size ever. But since that peak, due mostly to volcanic eruptions that spew bromine and other ozone-depleting gas, scientists have finally started to see the ozone layer repair itself. A study published in Science this year found the hole had decreased in size from the year 2000, and most of that decrease was specifically because of the Montreal Protocol, international policy for the win. Without the chlorine wafting up into the stratosphere, ozone is able to form naturally when UV light breaks up regular old oxygen from O2 into O3. Without that chlorine to mess it up, this process could restart. It can still be messed up by volcanic eruptions, but overall, without our meddling, the ozone layer may someday be back to normal. Based on this new study, the ozone layer might be back to 1980 levels by 2040. You can actually see how the ozone layer is doing right now on NASA's website. We will put the link in the description for you. Of course, this is science, so we can't all have happy endings. We still need ACs and fridges, and the replacement gas, HFCs, are a potent greenhouse gas. So now global warming is a concern. we can never win. But hey, at least a thing that we were fighting for as kids is now getting better, right? But why is there air in the first place? I mean...
Okay, did you write down everything you could and then watch the video? Make sure that you know that ozone layer protects us from the UV light. The UV light we know causes skin cancer and it hurts plants. And so we know where the ozone layer is found and it absorbs that UV in order to protect us. And we know that the CFCs that we produced in substances like Freon started to destroy those O3 molecules. Did you write that chemical reaction? Can you draw the molecules and the molecular shapes of those? So that's what I wanted you to write in your notes. Well, we know now, thanks to the Montreal Protocol, that we've replaced the CFCs. They were banned in 1995, and it really did make a difference for your future. But now, the HFCs. Let's see what you will have in the future. Okay, jumping ahead. So Roman numeral 2, what is the definition of chemistry? It's the study of matter. I like to say matter and energy, but we can also say, as your textbook shows, matter and the changes that it undergoes. And what's matter? Do you remember that from integrated science? Anything that has mass and takes up space, and we call space volume, right? Who studies matter? Organic chemists. There's lots of branches of matter and chemistry. So when we're talking about matter, we're really saying, what do chemists do? And there's a little blurb in your book. So go ahead and write some of these guys down. Organic chemists, anything with carbon is what they study. And so in general, it might be your second year in college that you would study organic chemistry, pharmaceuticals, plastics, any petroleum products within plastics. An inorganic chemist, this is what we're going to do most of the school year, is things that do not contain carbon. That's a salt crystal, by the way. But precious minerals, metals, nonmetals, gases can still be inorganic because they don't have carbon in them. Not all of them. Only petroleum products have carbon. And of course, huge field of semiconductors. A physical chemist studies the behavior of matter as it related to energy change and reactions and reaction rates. So what you see here is ozone added to nitrogen dioxide, and we're looking at the steps that take place in the reaction. We call that reaction mechanism and how fast it might actually occur. We'll talk about this in the spring, but there's something called physical. How about an analytical chemist? Somebody who really is looking at the components and the composition of a substance, kind of the quality of the substances, quality control. You're simply analyzing something without looking at the quantitative measures of it. So maybe looking at the nutritional value of food, or as I said, quality controlled. We'll do a kind of a lab final where we'll do a qualitative analysis at the end of the semester. And you'll get a little taste of this, kind of fun. What about a biochemist? So they look at matter and the processes in living organisms, really the biochemical reactions in your body, metabolism, or in a plant's body. Do you recognize that? Citric acid cycle, otherwise known as the Krebs cycle, in your dark reactions and photosynthesis. And of course, DNA and genetics, all of that is so much biochemistry. Okay, moving on, scientific method. You come across a plant, you're like, hey, what's going on with this plant? What's harming it? How would you design an experiment around it? This is what we call scientific method that you've seen so many times before. So let's review it real quick. I would like you to pause the video, take a minute, and find these words: experiment, observation, law, conclusion, hypothesis, theory. What order do they go in? And do you really know what each one of them means? Could you design an experiment for me? Pause me, write it down. Okay, did you say observation first? Now, make sure you understand the difference between an observation and an inference. Some of you on the first day of school, when you looked at that genie in a bottle, were saying smoke was billowing out of the volumetric flask. But it really wasn't a particulate of smoke. That was an inference and not an observation. You learned later that it was simply steam and it wasn't smoke. If you looked at a clock in the classroom, would you say the face of the clock is glass? No, because that would be an inference. It could be plastic, who knows? So when you do that candle lab, or if you've already done the observations of a candle, go back and look at your observations. Make sure they're true observations and not an inference. Okay, moving on. So we always start with our observations. Don't write this down, by the way, just kind of reviewing. Then we make a prediction or a hypothesis. I know you've done that before, kind of a cause and effect statement based on our ozone depletion. Let's just make up one. If more CFCs are present, then there would be less ozone due to the interaction of UV light. Oh, got the word of twice. That's okay. Anyway, cause and effect, a statement. If this is present, then that will happen. That's a good way to write a hypothesis to make sure that you've included your independent and dependent variables. You don't have to, but that's just an easy way to start. So if you were going to design an experiment, and I am going to ask you to in the candle lab, I'm going to ask you to tweak one of the steps. You always start with those observations, and then you make a prediction, and now we start to design that experiment. So let's think about an action. One of the steps in the lab had you turn a beaker upside down. If I can, there's my beaker. If I flip it over a candle, right, so that the candle is here, then we're really asking ourselves, okay, I observed that when I flipped the beaker over, something happened. Okay, let's design an experiment around that. How did you act on the candle? That's really your observation. So now what can you change? That's really your independent variable. What could we change here? Well, if that's what I'm observing, I could change the size of the beaker, right, and the amount of air. Now remember, one of the levels of your independent variable should also have a control. That's really important. So standard for comparison, and then different levels, maybe different size beakers, and let's call our control kind of somewhere in between, maybe what we started with. Then, how did you determine a response? That's our dependent variable. What are we measuring? In this case, maybe how long did it take before the candle went out? Time. There's a unit there with your dependent variable. Maybe qualitative and quantitative data. All right, and then we have what remain the same. So those are our constants, right? Candle size, the way to light it, things that we don't change, how we control that experiment. Not controls, but what we keep constant so we can actually measure the independent variable that we want to measure. And of course, when we take data, there's two types of data, our qualitative and our quantitative data. So in general, qualitative, a description, size, color, texture, and quantitative is a measurement to a standard scale. Did you guys use a ruler when you took measurements of the candle? I hope so. If not, go back and change it before you turn it in or before there's a lab check on that lab. All right, going through the parts of the scientific method then you're going to discuss your results in all your data. Put it together and really try to speculate, interpret what you saw. What does it mean? What do all those values in number mean? Then have a conclusion. Now, sometimes those conclusions are great and they might lead us to a theory. Theories explain things. If you look here, they are broad generalizations that are based on observation, experimentation, known for facts or phenomenon. And theories are created over a long period of time, after it's been tested for years, decades, centuries. Then we can come up with a theory that really is supported over time. What am I forgetting? Oh yeah, those laws. So laws are based on scientific facts that describe behavior of natural phenomenon. Can you think of some laws? Laws of gravitational force, right? When apples fall out of the tree. These are laws of nature. I really like to stress laws are based on natural phenomenon. So how planets revolve around the sun, gravitational pull, planetary motion, Newton's laws of motion as well, Kepler's laws, Newton's laws. These are all describing the natural world that we live in. Okay, we're almost done. Lab safety, which we'll talk about all week long, and you'll know all the safety rules, or at least how to keep me safe and you safe all school year long. All right, we're done. Write down some safety rules. Done with this homework assignment. Good job. Bye.